Okay, so let's get started, please. So, can anybody tell me what section 1.1 was about? What was section 1.1 about? Does anybody remember? Can anyone tell me, like, roughly what was it about? Yes, I'm sorry. Can you say your name, please?
Yeah, I'm Stella. I
Stella.
think we've got like the 6 of real numbers, and I'm just thinking about like natural numbers, rational numbers, inequalities, something like that.
Yeah. So there was this thing about numbers, and then there's, they started introducing inequalities. What else was in there? That may be it, right? There wasn't too much in it, but yeah. So it's basically starting with what are numbers, right? What are numbers? What are numbers? And so let me start off the way that I would probably start off. So I'm gonna so here's some notation that mathematicians I think all mathematicians are familiar with. This is actually due to this notation is actually due to somebody called Nicholas Bourbaki, who was a mathematician in the early 20th century, who wrote a lot of books, an incredible number of books, and published a lot of papers. Later, it became clear that Bourbaki actually did not exist. He was actually a collection of mathematicians all working together, and under the name of Nicholas Bourbaki. But for a while, people believed that it was an actual person. There was this sort of story of this old man, in France, Nicholas Bourbaki, and people would invite him to conferences, and he would always turn them down. I say, I'm sorry. I've seen actually a letter from him at Indiana University, and there's a letter from him on the wall saying, "Thank you for inviting me to your conference. I'm sorry, I'm an old man and I cannot attend." But actually, he did not exist. So yeah. But that group, wrote a lot of things and became very influential. I don't know if this will amuse you, but I had a friend in college who spent all his time reading Bourbaki in the library, and he eventually changed his name to Nicholas because he was so enamored of this style of mathematics. Yeah. Okay, so Bourbaki notation. There's this thing called so the natural n stands for the natural numbers. The natural numbers, and what people usually mean by them are the things like 1, 2, 3, etc. Okay. So I don't know if you've seen this sort of notation before. This is so-called set notation. The way you read this is the set of 1, 2, 3. The set including, or the set consisting of. The set consisting of 1, 2, 3, etc. Okay. Then people use the letter Z to stand for the integers. So integers, you know them. There's 0, 1, -1, 2, -2, 3, -3, etc. Right. So those are the integers. Right. People use Q to stand for the rational numbers. Rational numbers. Can anybody tell me what the rational numbers are? Anybody remember what the rational numbers are? Rational numbers? Yes, Stella.
I think there are ratios.
Ratios, perfect. That's why the hint is in the name, right? The rational numbers, they are ratios. So anything of the form, P over Q, where P and Q are in Z. P and Q are integers, and Q is non-zero. Okay, so let me read this in English. So I'm using more notation as we're going along here. So this is the way you would read this in English is the set of things that look like P over Q, where so this line is sort of like the things that look like P over Q, where this stuff on the right is satisfied. Okay, where P and Q are elements of Z. Okay, that is they are integers, so they are in this. People read this as in or as an element of. So P and Q are in Z. P and Q are integers. Okay, and Q is non-zero. Q is not equal to 0. Okay, so at the same time I'm introducing this Bourbaki notation, I'm also introducing you to some what's called set notation. Right. So a set is just a collection of objects. A collection of objects. So this is the set of natural numbers, right? It consists of all natural numbers, this is all the integers, this is all the rational numbers. Okay. Is everybody okay so far? I know that I'm sort of piling on the notation a little bit quickly. Don't worry, you'll become used to it. Anybody have questions? Okay. And then there's this thing R, which is the real numbers. The real numbers. Okay. And the author says, what are the real numbers? We're going to say that the real numbers are all numbers that can be expressed in decimal form. Okay. And you notice that these things over here were pretty easy to describe, right? Okay, at least they seem kind of easy to describe. Like these are things that you kind of know intuitively. We're a little bit cheating because we're using your childhood sort of intuition of what natural numbers are. 1, 2, 3, seem kind of instinctive to human beings, right? And then these things you introduce this negative. These things are ratios. Blah blah blah. But then this one is like has kind of a strange definition. All numbers that can be expressed in decimal form. Is there anything wrong with that definition? Is there anything problematic about that definition? How do you feel about this definition? Yeah.
Does it include like repeating decimal?
Yeah. So anything so for example, 0.12, 1, 2, 1, 2, 1, 2, repeating is a real number, yes.
It makes me wonder if it includes rationals, since a ratio can be converted into a decimal.
So definitely it includes the rational numbers, because these guys can be put in decimal form, right? These guys, all of these things can be put in decimal form. So these are all subsets of R. In fact, they're subsets of each other. So like the N is a subset of Z, right? These guys are all contained in here. These guys are all contained in here, and these guys are all contained in there. So we're becoming richer and richer as we go down here, right? And we're also what's happening is that we're sort of enhancing our ability to do things as we move down. So like here, there's a trouble with subtraction, because if you subtract 3 from 2, you leave your world, right? If you had only natural numbers, you would have some trouble with subtraction, right? Because they'd say, well, what's 2 minus 3? Yeah, and little children, of course, get really confused by that, right? Okay. Here, it's okay to talk about 2 minus 3. Once you get to this point, it's okay to talk about 2 minus 3. And so what this has is it has so-called additive inverses, right? Every number has its additive inverse. 3 has -3 that you can add to it and get to 0, right? Here you don't have additive inverses, right? You can't. There's no additive inverse for 3, right? And when we step from Z to Q, you notice that what we get here are multiplicative inverses, right? So you've got 3 and 1/3, right? You have things that you can cancel out multiplication, right? Here we can cancel out addition, right? You can add 3, but then you can add -3 and remove it, right? You can multiply by 3, and then you can multiply by 1/3 and get rid of that, right? So every step forward is kind of an advancement to what you can do within your world, okay? And then the real numbers, it's kind of strange. Like, what do you get? What do the real numbers have that the rational numbers don't have? Does anybody have an idea about that? Does anyone want to make a guess about that? What does R have that Q doesn't have? Yes. Square roots. Okay. Yeah. So you can take. It's true. You can take square roots. So yeah, that was actually. That's maybe not so obvious, right? Because you say like, are you sure you can't take square roots here? It's true. What you say is true. You like, there's no square root of 2 in Q, but there is a square root of 2 in R. That's actually the thing that's actually the question that got people out of Q. So the Pythagoreans, 2,500 years ago, stayed within the world of Q, and they believed that everything had ratios. Like the whole world was based on ratios. Okay, that it had this kind of harmony and beauty to it. But then somebody asked, "What's the square root of 2?" And that sort of overthrew everything for them, right? And the story is that they killed that person. Yeah, so there are multiple stories, probably none of which are true, but one story is that this person asked the question, showed that the answer couldn't be answered in Q, and then they threw him overboard. That's one story that I heard. Another story is that they figured that out, and he revealed it. That they figured out that there was something outside of Q, these square root things, and then he revealed it to the world, and then they killed him. So either way, the guy died. But anyway, so yeah, so square roots is one thing. Square roots is one thing. But to get the real answer to this question, you actually have to take some higher math. So it's like, actually not that much higher. So it has to do with these things called limits, which you'll learn in calculus, in fact. So yeah. So let me just say that it's actually really hard to talk about how to create the real numbers. Okay, these things are easy to define, but to define the real numbers is actually very tricky. So tricky to define. If people are interested, you can look up something. So one way of doing it is using something called Dedekind cuts. Okay, but I've actually never even read through the argument because it's kind of crazy looking. But yeah, so you can do it, but it's not so simple. And so the author admits at the end of the section, he says, we haven't done this section very properly, and this is what he's talking about. That we actually haven't talked about what these things are. Okay, talking way too much. Okay. Okay, so these are what we're going to be dealing with, numbers. Okay, so let me ask a couple of questions. Can somebody give me an example of a rational number? Somebody give me an example of a rational number? Yes. Emma. Yes. 2/3, right? 2/3 is great, right? 2/3 is definitely rational, right? Because, you know, it's p over q, and both p and q are integers, right? 2 and 3 are both integers, and 3 is not 0, right? So that's fine, right? Can anybody give me an example of an irrational number? Well, what's your name, please?
Amy.
Amy? Okay, Amy gave the example of square root of 2, which is actually not a rational number. So this means not an element, right? So not in. And square root of 2 is not in Q. Sort of along the lines of this course, maybe we should say, how do you know that? How do you know that? I think that's actually there'll be an argument sketched out in one of the homework problems about how you actually know that. I think it's the argument that the ancient Greek gave to show that this length here was not achievable within the rational numbers. Okay. Is 3.14159 rational? Got the question? Is that a rational number? Talk to somebody nearby for a minute.
You're so right.
Okay. Is it rational? Who wants to say? It's okay. Don't worry. You know, it doesn't matter if you're wrong or anything, actually. Right? So, okay. Why? So there's a no. Anybody else have opinion? Does everybody say no, or does anybody say yes? Okay, there's a lot of no's. Okay. So why? I'm sorry, I've forgotten your name. Fern, yes. Why no?
Because I don't think it could be expressed as a ratio.
Okay, yeah, that would be a good reason. So no cannot be expressed as some ratio, like some p over q, where p and q are integers and q is non-zero. Okay. What about 3? Is 3 expressible as a ratio? Okay, what about 3.1? Is 3.1 expressible as a ratio? What ratio is it for? What?
Like 3 and 1.
3 and 1/10 or 31 tenths, if you like. Right? So yeah, that's a ratio. Right? Are you changing your mind now? Yes. Right? So yeah, actually this is a ratio. You can express this as a ratio of integers, right? It would be 4159 0 0 0 0. Right? So if I've got the right number of zeros here. Let's see. 1, 2, 3, 4, 5. I think that's right. Okay. So yeah, actually that is a rational number. Yeah, any terminating decimal expansion actually is a rational number. What if I have something like 1 1 1 1 1 1 1 1? Is that rational? Is that rational? Yes,
Not if it's repeating.
Not if it's repeating. Okay. Actually, I'll talk to each other for a minute. What do you think?
Isn't that just the same as 0?
This?
No, the
This?
0.111 forever.
No, it's bigger than a half. I mean, it's bigger than 0.05, right? So,
Oh.
right. So, yeah, no. Okay, answers? Do people think it's rational? Irrational? Yes. Please tell me your name.
My name's Janie.
Jane.
Yes, it is rational.
Yes, it is rational. Other answers? People think it's not rational? Okay, Janie, why do you think it's rational?
I know there is a way to get that number through a ratio.
To express it through a ratio.
Yes.
Yeah. So actually, as I overheard you say, it is 1/9.
Yeah.
Yeah. So if you divide 1 by 9, this is the number you get. One way you can see that is to multiply. Let's call this thing x, and then look at 10x. 10x would be 1.11111111 repeating, right? And then x is 0.1111 repeating, right? And then you can see that 9x is 1, right, by subtracting, right? So this minus that gives me 9x on the left and 1 on the right. So x is 1/9. Okay, right? And similarly, if I look at something like 0.1212121212, you can see that if we multiply that by 100, let's call that thing y, 100y is 12.1212121212, and y is 0.12121212. And you subtract, you get that 99y equals 12. In other words, y is 12/99. Okay, so what you see, what you can suspect and probably realize is that if you have a repeating decimal, then you're guaranteed that it's rational. Okay, so rational numbers, repeating decimal means that forces it to be rational. And I've just introduced a little bit more notation. This double arrow means then. Okay, so if this is true, then that's gonna happen. Okay. In fact, it's true that that it goes the other way as well. So if it's rational, then you're guaranteed that it's a repeating decimal. Okay. So if you're thinking about the real numbers, then if the real numbers are, as the book says, the guys with numbers with decimal expression, then the rational ones are the ones with repeating decimal expressions. And then the irrational ones are the ones with non-repeating. Okay, so the irrational ones are the non-repeating ones. The rational ones are the repeating ones. You don't have to know that. I'm just telling you. It's just something cool. Yeah. So people say, one fact that you may have heard is that pi is irrational, right? Like the square root of 2 is irrational. And from what we just said, that irrational means non-repeating. So that tells you actually that pi, the expression for pi never repeats. Okay, does not settle into a repeating pattern, because if it did, it would be rational. Similarly, the square root of 2 is not going to settle into a pattern. Okay, it's not going to settle into a repeating pattern. So, like, you might think, 14159, whatever. You might think, maybe at some point it starts repeating. No, if it did, it would be rational. Okay. Similarly, square root of 2, 1.4142, whatever. that's also not going to repeat ever. And you can make up irrational numbers as you please. Just make up some pattern that doesn't repeat, right? And now that's going to be irrational. And anything with a repeating pattern would be rational. So okay. So sorry, I'm gonna stop there. Yes.
What's another example of
An irrational number? Yeah, so in your book, they actually make this comment in the homework that if you take any number that's not a perfect square and take the square root of it, that's going to be irrational. Yeah, so of course the square root of 4 is, because 4 is a perfect square, you get 2, right? But anything other than the square root of a perfect square actually turns out to be irrational by an argument basically identical to that of that ancient Greek person who got killed. Okay, so we'll finish the rest of the section next time, and we'll go on. So yeah, okay. See you all next time.